Good afternoon to everyone. My name is Cinzia Bellezza. I will chair this session. Thank you for joining us. This webinar, the title of this webinar is New Italian Facilities for CO2 Capture and Utilization. Sorry, but I have a problem. I can't go on with the slide. Sorry. I need some help from the organization.
Prova a dare invio o freccia a destra.
No, non funziona. No, it doesn't work.
Dammi il controllo. Richiesta.
Okay. Now I think I can. Yes. Now it works. First of all, some recommendations. All the participants must switch off their microphone and the camera during the webinar. The questions are welcome at the end of both the presentation session. And please type the questions in the panel questions, and please indicate the name of the speaker to whom you want to ask the questions. And then the speakers will answer you. A brief introduction about ECCSEL ERIC. ECCSEL is the European Research Infrastructure for CO2 capture, utilization and storage. The aim of ECCSEL is to enable low to zero CO2 emissions from industry and power generation. The 5 countries are part of ECCSEL: Norway, France, Italy, United Kingdom and Netherlands. ECCSEL includes 28 research facility owners, providing open access to more than 100 world-class research facilities. ECCSEL is continuously expanding with new members and partners and facilities. From 2015 until 2030, upgrade and new builds in the range of 200 million euros are planned. So the objectives of ECCSEL are close CCUS knowledge gaps, contribute to reduce the CO2 emissions in accordance with the agreement of 1.1.5 degrees target, and at the end reduce the global warming. This webinar is organized in the framework of the Accelerate project. Accelerate was a 3-year project, but it has been extended, so now it is a 4-year project managed by ECCSEL ERIC. The end of the project is December 2023. The budget 3.5 million euros. The project Accelerate focuses on increasing use and long-term sustainable operation of the ECCSEL ERIC research infrastructure, developing marketing, access and services models for the industry and small-medium enterprises, increasing international collaborations, extending ECCSEL ERIC activities towards the utilization of CO2, so from CCS to CCUS, where U is utilization, developing national nodes and expanding ECCSEL ERIC membership, and increase the involvement of the ECCSEL ERIC with ongoing research industrial CCS projects. In the framework of the Accelerate project, there is a capacity building program. The capacity building program consists of 3 main core activities: a webinar series dedicated to highlight some key topics of capture, transport, utilization, and storage, specific workshops held in conjunction with popular summer schools such as Panarea and Sulcis, and also tailored training courses addressed to attract industry, researchers, and new user groups to ECCSEL ERIC. Today's agenda includes 2 speakers. The first, Michela Alfè. She's a senior researcher of CNR STEMS, Institute of Sciences and Technologies for Sustainable Energy and Mobility. And then Giuseppe Bonura. He is also a senior researcher of CNR, ITAE, Institute for Advanced Energy Technologies, Nicola Giordano. So now, Michela, the floor is yours.
Thank you, Cinzia, for your kind introduction. Okay. Oh. Can you see the screen?
Yes.
Okay. My name is Michela Alfè, and I'm from CNR STEMS. And in this frame, I'm going to introduce our facilities, our brand new facilities belong to the ECCSEL network. Our facility is devoted to CO2 capture by sorption on solid sorbents, and it is named Material Development for CO2 Capture, briefly made for CO2. Just few notes about CNR. The CNR is the National Research Council in Italy, and it is the largest public research institute existing in our country. And it is the only one under the research ministry, and we perform multidisciplinary activities spread all over the human knowledge. We are now 100 year of activities. This year we are celebrating our 100th anniversary, and we are, as you can see from the map, widely distributed all over the Italian country. What about the number? We are a lot of researchers. We are more than 8,500 people involved in CNR activities, among researchers, technicians, and administrative staffs. We are gathered in 7 thematic departments, and okay. My institute belongs to the Engineering, ECT, and Technologies for Energy and Transportation. My institute, STEMS Institute, has 4 sites for location in Italy. We are laboratory specialized with a lot of advanced equipment, and we are different sites of plants spreading from laboratory scale to the pilot scale. We are currently involved in national and international research networks, and we are about 150 persons among researchers, technicians, and administrative staffs. Our site, the site of my institute, my location is Naples. Other sites are Torino and Ferrara in the north of Italy. The research areas covered by STEMS Institute are reported here, and the area of the facilities I'm going to introduce is the red one: innovative catalytic processes and advanced materials. Okay, just a few lines about our approach to the development of new concept materials. We are focused on the implementation of eco-friendly and cost-effective synthesis protocols of sorbents and materials, and we focus on wet chemistry approach. This is because this kind of approach guarantees us cost-effective and scalable possibility to produce material in large quantity. We are skilled to develop materials from design to the chemical formulation to the production and implementation of the properties of material. And to do that, we adopt a multi-scale approach involving a lot of competencies among chemistry, physicists, and engineering. Our materials are developed in a circular economy perspective. We are focused in this kind of approach because from the design of the material, we focused on the scalability and the possibility of valorizate the raw materials to engineering materials, and our materials are produced and are designed to be recyclable. So we have a open eye to the perspective of the circular economy. We work in this kind of circular route, starting from composite design, manufacturing. We also use specific deposition of the material on given substrate, and also we also focused a lot of the recovery of the raw material after their use. We also think about the end use of the material, the fate of the material after their use. Okay, these are the main research lines and the application of the advanced material we are producing in our institute. Advanced material are devoted to a lot of applications. For instance, a sensitive and conductive thin film for VOC and oxygen and small molecules detection. We produce photoactive materials for catalysis and other possibility. We produce materials suitable for coating, also for coating of non-planar and living surfaces, cells and small particles, biocompatible and bioinspired materials, materials for water remediation, such as heavy metal capture, and also rare earth elements. And last but not the least, materials for CO₂ capture and storage. In this frame, we are developing the made for CO₂ laboratory. Just insight, just to give you some insight in this our approach, some of these materials. Just two brief examples. For instance, we are going to produce materials for CO₂ capture in real condition, practical condition, and also in harsh condition. For instance, a fluidized bed application. Working on the surface, we work on materials from renewable raw materials and feedstock, char, carbon black, and so on. We functionalize this surface, this porous surface, to give the surface a specific functionalization and coating suitable to enhance the performance for CO₂ applications. For instance, we produced since many years materials coated with ferromagnetic particles and a lot of active sites for to enhance the acid-base interaction with CO₂. All the materials are, as I told before, specifically designed to be fully regenerated after every CO₂ absorption cycle. Another line of research is the development of a crystalline porous framework, the metal organic framework, and hybrids. The metal organic framework are very, very interesting materials for CO₂ capture and gas sorption application, since they are a very high surface area, water stability in most cases, simple and scalable procedures of synthesis, and all the precursors and the overall synthesis are approachable to low cost. They also assure full regeneration after use. Just to give an idea of the flexibility of these materials, metal organic framework are basically composed by metal ions linked with ligands. Here, metal organic framework can assume a 3D polymer network. We can change the size, we can change the shape, just acting on the synthesis procedures. We can functionalize the surface by simply conjugation chemistry approach. And also we can, after use, post-process this metal organic framework to obtain porous metal oxide materials for other or similar applications. Just to give an idea of the flexibility of the shape and internal of the performance, just having the same ligand and changing the metal inside the metal organic framework, you can obtain different porous structure and different shape, specifically thinked for CO₂ applications. Another approach we are currently using in our group is to embed inside the metal organic framework, inside the structure, active molecules such as graphene or graphene functionalized with other molecules. As you can see, the possibilities are very, very huge. And also, after post-processing, you can obtain a wide array of functional materials. Okay, going to the Made for CO₂ laboratory. This new lab will be located in Naples, in our headquarters in this big building, and this laboratory will host facilities for the synthesis in lab scale of new materials for CO₂ capture, characterization of the performance in terms of absorption of CO₂, and testing. And we can follow all the CO₂ chain and the absorption fate of the materials, from the design to the post-processing to the end-of-life material. The area of the research that the facility will support are decarbonization and energy transition, development of sustainable technology and circular economy, innovative catalytic processes, and advanced materials. What about the instrument that will be hosted in these facilities? We will have lab-scale facilities for material synthesis, including furnace for pyrolysis and carbonization of raw materials, for instance, biomasses, hydrothermal carbonization reactor to obtain a thermochemical conversion of wet feedstocks. This HTC reactor will enable us to use wet feedstocks without the thermal treatment needed to water elimination. A spray coater to functional coating of solids. This is very, very useful to obtain a solid, a functional film on a scaffold, on a designer scaffold. So to lower the costs by lowering the active materials need. And regarding the characterization, we will have an X-ray photoelectron spectroscopy, a breakthrough aimed to the characterization of the surface of these materials, because the characterization is fundamental to link performance and activity. The breakthrough selective absorption analyzer to the assessment, to obtain the assessment of CO₂ performances of the solids under dynamic flow, so under very realistic situation and conditions. An atomic adsorption spectrophotometer that will be aimed to the characterization of the material in terms of elemental composition. A stylus profilometer for the surface characterization, and of course an high performance gas absorption analyzer to obtain a clear picture of the pore size, surface area, and pore volume of the materials and powders. A thermobalance equipped with an autosample coupled with a transfer line with an analyzer of infrared type. This is very important to obtain a clear idea of the thermal performance of the material and also of the evolution of the material after a thermal treatment or under dynamic condition. And at least an electrokinetic analyzer that will be very, very useful to obtain a solid surface analysis in terms of surface charge. The charge of the material is very important because the interaction with CO₂ is an acid-base interaction. So a clear idea of what happens on the surface of a solid is fundamental to assess the performance of the material in terms of CO₂ capture. Okay, just final remarks. These big facilities we are going to build in the south of Italy. In our idea, will offer the opportunity for all people interested in to produce, characterize, and test materials and sorbents in conditions mimic real operation. And all the people who would like to join this facility will make use of our consolidated experience in the development and synthesis of multifunctional material and preparation. As I told before, the development of material starts from the design, from the chemical formulation, to the production of a physical object in a very structured form. In this way, we will use, of course, a multi-scale approach. Sustainability of the approach and production is a keyword of our laboratory. And also, we will take an eye to the optimization of the sorbents from the point of view of the cost-performance ratio. That's a very, very important goal. Okay, we will be the first Italian node in the south of Italy, specifically devoted to this kind of application. And we expected to be fully operative with all the equipment and all the facility in site and fully operative from the first semester of 2025. Just a projection of what we expected per year in terms of availability. Of course, it's a variable number based on calendar activities, but it's a minimum of 6 weeks. Okay, I think this is all for my side. Thank you very much.
Thank you, Michela, for this interesting presentation. Now, Giuseppe, the floor is yours.
Thank you, Cinzia, for your kind introduction and for this space, this opportunity today. Good afternoon, everyone. Good afternoon to all the participants. I'm Giuseppe Bonura, Senior Researcher at CNR, Institute for Advanced Energy Technologies in Messina, in the south of Italy. What I'm going to show you are a few slides about the main features of our facility, which is under implementation in our institute, with the aim to offer complementarity of aspects with other facilities already included in the ECCSEL infrastructures in the area of carbon dioxide utilization. In particular, the main idea behind the GTL for CCU is to create an open green tech lab for carbon capture and utilization applications. Let me to skip the introduction about the CNR, already introduced by Michela. Only I would like to underline the specific mission at ITAE. Nicola Giordano is the name of the founder of our institute. Well, the mission is related to the development and promotion of environmentally friendly power technologies and sustainable processes, this mission is delivered under 5 main thematic areas: transformation and storage of thermal energy, production and storage of electricity, production and storage of hydrogen and environmentally friendly energy carriers and technologies for carbon dioxide recycling and utilization, application of the integrated system for an enhanced energy efficiency, and socioeconomic and environmental impact of energy technologies. My research group at ITAE in Messina operate within the green box, so specifically about the production of environmentally friendly energy carriers and technologies for carbon dioxide recycling and utilization. In particular, our skills are delivered in the field of the development of novel solid catalysts for the production of alternative clean fuels. Basically, it means the components of my team have a specific competence about the preparation, characterization, and testing of solid materials for the production of alternative fuels. These fuels are typically produced according to 2 main research lines: gas to liquid processes, concerning the catalytic hydrogenation of carbon dioxide in presence of a solid catalyst for the production of methane or liquid organic hydrogen carriers like methanol or dimethyl ether, and the biomass to liquid processes for the production of biofuel be a conversion of biomass or bioderivatives into in a liquid-solid catalysis. So this involved the production of biodiesel, the valorization of the byproducts of the chain, like glycerol, and also the wastewater management by technologies performed in supercritical fluids. Well, on this background today, it's my pleasure to introduce you the unique features of our GTL for CCU facility, which we are implementing by an important upgrading and revamping of the existing infrastructure. The main objective is to offer latest generation device and equipment based on cutting-edge technology to establish a unique environment entirely devoted to CO₂ utilization. So from the preparation of solid materials, their characterization, and then their testing in hydrogenation processes for the production of net zero emission fuels. The specific challenge is to design, to synthesize novel materials by unconventional procedures in a readiness level ranging from 3 to 4, 5 by additive manufacturing of 3D materials, beside to advanced characterization and testing at lab scale or pre-pilot scale equipment. Here I call some bullet points to emphasize the specific advantages of the services provided within our research infrastructure with respect to the state of art. So what we expect from the implementation of these facilities is innovative synthesis routes to prepare multifunctional catalysts suitable for CO₂ activation, breakthrough characterization techniques applied to study the catalytic processes of CO₂ hydrogenation under real conditions, that's very important, highly localized characterization of hybrid samples by latest generation microscopy, enhanced efficiency of reactor configurations and continuous operation for evaluation of catalyst performance and lifetime, training of young students or scientists in the field of CCU technologies. Basically, GTL for CCU is so divided, split in 4 main pillars, so all of them focused on development of innovative catalytic system for an efficient conversion of CO₂ into e-fuels in a continuous feedback between kinetic study and thermodynamic prediction. Here you can read the 4 pillars, starting from the first one, design and preparation of powdered structural materials with thermal properties, advanced optical electronic microscopy to investigate the structure, morphology, and architecture of solid materials, in situ and operando techniques to analyze the activity selectivity pattern of the catalytic system under relevant conditions in order to get mechanistic use in view of optimization. Lab scale test rigs equipped with the fixed bed steered reactor to study and validate the catalytic behavior, their performance, and their stability during CO₂ hydrogenation into e-fuels like methane, methanol, dimethyl ether, or synthetic hydrocarbon for maritime or jet fuels application. First pillar, catalyst preparation, includes different installation. In particular, the development of a solid catalyst for an efficient CO₂ conversion takes advantage from an innovative, customized robocasting machine for additive manufacturing of 3D hybrid catalyst. The study of the suitable rheological properties of the printable catalytic pasts is then validated by a Turbi-scan analysis. It's very important in order to have materials with proper consistency for printing. The catalysts are typically shaped as powder, pellets, or matrix-like structure. As an auxiliary service, a proprietary customized 7-liter filter reactor is already available for scale-up of catalyst synthesis in one single pot. I mean, the typical phases performed for the preparation of a catalyst, thanks to this innovative equipment, can be delivered in one single pot. So precipitation, washing, filtration. And obviously this is time-saving equipment. Pillar 2, this is an area completely devoted to microscopy. In particular, we have here different installations to provide the services for digital optical microscopy with an all-in-one system for view, capture, and measures at 2D or 3D level on samples even with an irregular surface. However, our flagships are the transmission electron microscope field emission gun instrument, able to deliver a punctual resolution minor than 0.2 nanometer at 200 kilo electron volt without aberration correction. The instrument is already available and is working. Already it is in full service, and moreover we have also purchased an ultra-high resolution field emission scanning electron microscope equipped with the focused ion beam FIB source and detector stem. This installation will be likely completed by the end of the year. Concerning the pillar 3, here we have an in situ operando infrared installation for advanced materials characterization. The main installation include latest generation infrared spectrometer equipped with an environmental chamber able to work under high temperature, I mean up to 800 Celsius degree and up to 30 bar, to monitor the evolution of surface species and intermediates under real conditions. So we can follow, monitor the evolution of a specific process on time. The infrared spectrometer is also joined to a mass spectrometer and a thermogravimetric machine in an approach of hyphenated technique for a comprehensive analysis of the reaction pathways of the whole catalytic process. By the end of the year, an environmental chamber for diffraction analysis will be also available for the upgrading of our diffractometer for in situ investigations. Last but not least, pillar number 4, regarding the catalyst testing equipment, the research facility is completed by different lab scale or pre-pilot scale plants, integrating tubular and stirred reactors for the production of methanol, dimethyl ether, higher alcohols, or hydrocarbons from CO2 conversion in presence of green hydrogen. What you can see is the image below on the left bottom, is the image of a bench scale rig allowing the utilization of a dual reactor setup for faster processing of catalyst materials, resulting as a cutting-edge technology in the existing market. Additional services include the stations for solar fuels and water splitting, electrochemical cells and stacks for photo and electrocatalysis studies, electrochemical impedance spectroscopy, inline GCs with the automated ghost sampling loop for gas analysis. So let me in the end to thank the financial source behind this facility, taking advantage especially from the excellent research infrastructure project. Many thanks to the components of my research team at ITAE, and wishing to also you soon in Messina behind your application for access in our new GTL for CCU facility. I thank all of you for your kind attention. Thank you.
Thank you. Thank you, Giuseppe, for your interesting presentation about e-fuel from CO2. Are there any questions from the audience? If yes, please, you can type them in the answer and question and answer panel or in the chat. For now, no questions. I have a question for both of you, Giuseppe and Michela. From your presentation, it is clear that the research about CO2 capture and CO2 utilization is really at a high level. But what about the transfer of this knowledge to the industries, for example? So what I'd like to ask you is, do your institutions have contacts with the industries for a sort of technological transfer?
Okay, Cinzia, thank you for your question. This is a good point. Obviously, as a research organization involved in many research projects, we have established a lot of international collaborations with not only small and medium enterprises, but also large industries, in order to put our research findings on a higher level than fundamental research. In this frame of CO2 utilization, we are proactive in finding a new solution for future or fast application of discoveries into the market.
Okay, I would like to add something about the to the answer of Giuseppe. Our institute is highly connected with all the smart grid concept in terms of the fate of CO2 from the production to the capture and to the valorization into other, also in terms of CO2 materials. So yes, we have as an institute, as a STEMS institute, a huge connection with all the productive system in Italy and abroad. The problem of CO2 is a very, very huge problem for humankind, and it is important to face this problem for looking at a new perspective and looking at the problem from a lot of point of view. This is our goal, and this is what we are going to do with this huge facility implementation in the south of Italy, thanks to ECCSEL, thanks to the financing, the funding of the EU.
Thank you, Michela and Giuseppe. We have another minute for questions from the audience. Oh, one question. Energy need or something else is the questions for both of you, I think.
I can't catch the meaning of the question.
Yes, we need more details about this question.
In terms of sustainability of the facilities, you mean? Or of the process entirely? Or the whole process of CO2 capture?
Obviously, the research infrastructure or the new facilities within the research infrastructure take advantage from the existing building and installations already available in our institutes. So minor energy needs is required for further implementation or upgrading or revamping of our plans. I don't know if I replied to the question.
If you mean the sustainability of the process of CO2 capture through this approach, okay, it is under continuous study. We are working at relatively low TRL, but hopefully this is one of the best possibility at the moment.
Something else? I really, could you please type a little bit more so we can understand better the questions, please?
You can enlarge the question field by clicking on the small icon near the X on the tab of the question field. That will make larger, so you can.
The question is for Michela. A question on method for CO2 lab. By improving the performance, you mean to increase the capture rate, the energy need, or something else?
I cannot catch the. Okay, from the panel of the chat, I cannot catch the. Okay, can you please repeat the?
Probably you are not reading the entire question. Yes, a question on made for CO2 lab.
Okay.
By improving the performance, you mean to increase the capture rate, the energy need, or something else?
Ah, okay, the capture rate. Capture rate. Okay, basically, this lab will be devoted to the design and optimization of the performance of materials for CO2 capture application. So when I say performance improvement, I mean the performance toward CO2 capture performance. Of course, you can capture CO2 through material with different technologies. Each material could be optimized for a specific application. I mean, if you work at low pressure, high pressure, mid, high temperature, and so on. There is a specific material, a specific optimization of the material that can be conducted to optimize the performance to capture more CO2, but not only about the charge of CO2 per square meter for each material, but also to improve the cyclability of the material, the possibility to use the material in repeated cycles, to use the material at low costs of production. So there is a lot of room of optimization of the performance. You have to look to a lot of aspects of performance implementation, I mean.
Thank you, Michela. I don't know if there is another question.
Yeah,
Perhaps
there is another question by Andrea Iove, but he didn't specify for which speaker, so I'm going to read it. Could you mention some number about productivities for EX? Sorry, that seems incomplete. Methanol. Could you mention some number about productivity of methanol for X? And I'm not able to read the rest because it seems incomplete.
But the productivity, obviously, of the productivity of methanol obviously depends on the feedstock you are using, because it dramatically changes from the carbon dioxide conversion to syngas conversion. So it depends on the CO2-rich gas stream. But typically we can overcome the classical 800 gram of methanol produced per gram of catalyst per hour. Obviously, not only the operating conditions, but also the specific catalyst composition can drive the final result.
Andrea also asks about the condition of tests.
The condition the test typically can be performed in a large variety of conditions, but typically from an industrial point of view, methanol synthesis is performed above 70 bar. But we can achieve the same results by operating at milder conditions. I mean, in the range of 30-50 bar, and in a range of temperature compressed between 200 to 240 Celsius degrees in presence of a classical copper-based catalyst formulation.
Cinzia, there is also a question.
Yes, now I see it. There is another question from Felipe Rios.
I can read the
okay.
Now I can read the chat. It's a very nice question, because Felipe is asking if the Made for CO2 lab is aiming to research on materials to be used in downhole storage. as CO2 is very corrosive at downhole condition. Okay, no. We intend to use the materials outside the storage. We use the materials as carrier of CO2, not for permanent storage, as a carbonate and so on. The idea behind these fine development materials is to conceive a material that can carry and concentrate CO2 to be compressed and stored. So the material is just a kind of catcher for CO2 in order to produce CO2, pure CO2 to be concentrated or use it for CO2 metallization and other application. So the material is not intended to be used for direct storage into holes and in reservoir.
Thank you, Michela.
Thank you.
Are there any other questions? No. So thank you, Michela and Giuseppe, for your very interesting and high-level presentations. For the audience, thank you for having joined us, and we are looking forward to see you at the next webinar next week. So thank you, and have a nice day.
Bye, thank you.
Thank you to inviting us, and see you.
Thank you.